Welcome to a very interesting physics topic on periodic motion. There are lots of things in this world that vibrate, oscillate, move back and forth at a constant rate. And the question is, what are the physics behind it, and are there any patterns that we can establish? It turns out there are some very special systems that exhibit something we call simple harmonic motion, and we're going to explore that to start with here. And just to blow your mind, watch this for a minute. Let's go back to our good old friend, the uniform circular motion around a circle. First of all, what does the word uniform mean? The first time we came across uniform was when we were talking about uniform acceleration. Of course, the classic example is when you're in a uniform gravitational field, which means constant. Uniform means constant. An object free falls at a uniform rate of change in our velocity, our uniform acceleration. So we developed some equations for that. Later on, we saw that another uniform situation was an object moving around in a circle. You remember our good old friend, the ants on the fan and the ants on the bike wheel. And if the bike was traveling along the road at a constant speed, then the wheel rotates at a constant angular speed. For example, in 20 RPM or something like that. And so what's uniform about that? Well, the angular speed in RPM or radians per second is constant, as is its tangential velocity. Now you might wonder, well, how does this relate to periodic systems? Well, certainly this is a periodic motion that we have going on here. But what about a pendulum? Does this look like a pendulum at all? Not really. So let's see what comes up later on. So back to our worksheet that you did before this chapter. This looks very similar to the unit circle that you studied in trigonometry, and of course that's where this comes from. So we have a circle of radius r, and I'm starting at some random point up here as our initial position. We could also call that our initial angle, and this object is going to move around the circle counterclockwise in uniform circular motion. And the first question is, how could I find the position theta as a function of time as we move around this function? And if you remember back to when we were working on uniform circular motion and the motion equations for that system, it was pretty simple. Well, we start with our angular velocity, which is counterclockwise, and if we go some time t in the future, our object might end up over here, for example. How do we know how far it's traveled? What would this angle be from here to here? Well, it's just your number of radians per second times the number of seconds you travel. And so we have our simple equations for motion here. Go back to motion equation 5. It's our velocity times time plus our initial position. You'll notice there is no acceleration term here because this is uniform circular motion. Otherwise, we could have a 1/2 alpha times t squared to bring in a radial acceleration if we wanted to. So now that we know that, let's go ahead and figure out what the position versus time equation is for just the x motion of this object. This object's moving around in a circle, but it is moving left and right at the same time it's moving up and down. So let's figure out what the x component of that is. Well, that's easy enough. Let's break it down into components. And there's our radius, and we're going to just break this down into a right triangle. Here's our x component that we're looking for, and later on we'll use this as our y component. And of course, what's our x component from trigonometry? It's r cosine of theta. But of course that theta is changing with time, so we can just use this for our theta, and we come up with this parametric equation. This is our position with respect to time, and it's a cosine function. Why does a cosine function work for this? Well, let's just assume our initial position is 0. All right, let's assume we started right here. Now remember, for cosine, when cosine is 0, we get a maximum value for x, and we're moving back and forth on our x-axis here. And so our maximum value would be right here. So cosine seems to fit our maximum value. If we go 90 degrees, we'd be up here, which on our x-axis is just down here, which would be a 0. And so cosine of 90 is 0, so it looks like it matches quite nicely. And it does. And in the same sense, we can repeat for the y motion as well. We can come up with the height at any point in time is r sine of theta, and to get the time component in here, we can replace the theta with our equation number 5 that we have up above. And that'll map out our y as a function of time. So let's map this out. Let's trace the object's motion in the x direction. So this one moves a little bit fast. I apologize for that. But as you can see, as this thing moves counterclockwise in a uniform speed, our object swings left and right in a very regular periodic motion. In the y direction, this is a little bit nicer animation because it goes a little bit slower for you. And as we move around the circle, the object's moving around the circle, but if you just look at the y component of it, we can see it moves up and down and up and down. So what if you were to trace this position of the object over time? What would it look like? What mathematical shape would you see? Well, it's going to look like that sine curve that we pulled up here for the up and down piece. And if we looked at the cosine function, and if we turned this diagram sideways, we'd see something similar where this thing is tracking back and forth downward. Alright, so let's take a look at this and let's ask ourselves some questions. Does the object move left and right or up and down at a constant speed? Well, let's take a look at the slower one, a little bit easier to see here. Is this a constant speed or not? Well, it can't be a constant speed because we have to stop and turn around at the top and the bottom, so it's not a constant speed. In fact, it's probably going to be moving the fastest if you look closely right in the middle here. And then it slows down, stop, turn around, stop, turn around, fast, stop, turn around, fast, stop, turn around. In fact, what we can do is we can just use a little bit of calculus or slope work and take the first derivative of our position function to get our velocity function. Let's remember that the derivative of cosine of x is negative sine of x. But we don't have a simple old cosine of x function here. We have some lump. We have a larger function in here, and we're going to use substitution for this. Use the chain rule. And so I'm going to take the derivative of cosine is negative sine of our original operand in here. And then I'm going to take the derivative of omega t plus phi. And remember, this is a constant. Omega is a constant. And there's our dt for our derivative. And this is a constant as well. So that's going to drop out as a 0. And we get this, our chain rule gives us this omega which pops out front. And of course, now we can see our velocity is not a constant. It varies with time in a sinusoidal manner. And in fact, it's the opposite sign of our position function. So we'll examine the acceleration on a physical system a little bit later. It's easier to explain there. But let's just take the derivative and see what it looks like. And once again, the derivative of our velocity function, dv dt, gives us acceleration. Or the second derivative of the position function gives us the acceleration. And I'm going to take the derivative of sine. The derivative of sine is cosine. No sign change is going to happen here. We'll just carry the rest of this down with us. And I have to use a chain rule, and so the derivative of the inside is going to give us another omega that we're going to pull out front. And what we get is negative omega squared cosine omega t plus our what we call a phase shift right here. Now you'll notice that the position and the acceleration, since they're both cosines with the same angular frequency, they're going to be moving together. And the sine is going to be doing just the opposite. Whenever this is at a maximum, this is at a 0. Whenever this is at a minimum, this is at a 0, and vice versa. And we can do the same for our y function as well. We can calculate what the velocity and the acceleration is just using a simple derivative. Let's take a look at a physical example of uniform circular motion. Let's go back to our ant on the bike tire. And this bike tire is about 50 centimeters across. And I spun it very quickly, and it is running at roughly uniform circular motion. It's a very low friction bearing, and so this should be, I only run it for about 5 seconds, and so you'll see it runs several times through 5 seconds. And let's see what happens on Logger Pro. Here's the video first. And as you can see, we're going on at quite a nice clip here. And what I did is I stuck a label on the wheel so I could track it using Logger Pro. So here's our Logger Pro data. And as you can see, it looks like a pair of sinusoidal functions. I apologize for the color change on the previous a couple slides back, I was using red and blue for the opposite sign functions, but LoggerPro does what LoggerPro does. And I ran a regression fit, and it fits very, very nicely to sine and cosine curves. And you'll notice there's an A, B, C, D. A is your amplitude, B is your angular frequency, C is your phase shift. And I'm going to ignore any phase shifts that we have here. And actually what I can do with a phase shift, as you'll notice, these phase shifts on these, let's see, where are my phase shifts here? My phase shift here is about pi, and my phase shift here is about pi over 2. So what I've done is I've eliminated these phase shifts just by using a trigonometric identity. And what I've done is come up with the position versus time in the x direction as 0.25 cosine of 14.1t. The 14.1 is coming right from my regression. And you can see I'm starting at on the x-axis, which if we turn this sideways, look at the x-axis, starting at the right, and then moving forward, and then coming back down and coming around, coming back down and coming around. In the y direction, we get negative 0.25 sine of 14.1t. The 0.25 comes from the fact that our radius is 25 centimeters. And if we convert the 14.1 radians per second into RPMs, we find out it's 135 RPMs. Now, one thing you might ask yourself is when I drive the uniform circular motion x and y parametric equations, they look like this. But you'll notice that I ended up with a negative sign for the y value. And if somebody can explain why that happened, I'll give you 2 bonus points. First come, first serve. Here's another simple example. Let's say we have an object rotating at 20 RPM in a 160 centimeter diameter circle. Find the parametric equation for the motion. And so there's our object moving, and we're assuming it starts right here. And once again, I'll calculate our omega is 2.09 radians per second. And I can just plug into our equation here then using our initial conditions of 0 for the initial position. And I'm sorry, I should have divided this by 2. This should be 0.8 cosine of 2.09t because this is a radius of 0.8 meters. In the same sense, we can do the same for the y equation, but just remember I made a little mistake here. This should be 0.8 in terms of our radius. So this should be 0.8 radius. All right, let's look at a totally unrelated system here. What I've got is a frictionless surface, and I've got a mass, and what I've done is I've attached the mass to a spring. And if the spring is just sitting there, not pushing or pulling on the mass, the mass would be sitting right here at the 0 point. That's what we call our equilibrium position. And it's very important that you know this terminology. So, and what I do is I stretch this block back all the way to this maximum position over here, and then I let go. And it's going to go flying to the left. And I'm showing you at some point later in time, it's on its way back to the left side here. Let's just remember that we are using an ideal spring here, and just remember as we pull the spring back, the force on the spring changes. It's F equals minus kx. And so the further we pull that spring back, the harder it's going to pull. I'm going to use that dot to represent our block at time 0 when we stretch it all the way back. And what's going to happen when we let go? Well, our spring is going to be pulling with quite amount of force to the left, towards the equilibrium position. All right? And then I let go. And when I let go, that object accelerates to the left. Its velocity is 0 here, and its velocity is, which is represented by this blue area, is quite large over here. And as you noticed, I'll run it again for you. As I move towards the equilibrium position, our spring force is dropping to 0 at this point. Maximum spring force on the right side, which means maximum acceleration, and 0 at the equilibrium position as we pass through that point. And so our acceleration in the middle should be 0. If we continue, now we pass the equilibrium position, and now we're actually compressing the spring over here, and the spring will be pushing to the right back towards the equilibrium position again. And so let's see what happens as it passes the equilibrium position. as an aside here, this spring force in this situation, you'll notice when we're on the right side of the equilibrium position, the force acts towards the equilibrium position. And when we move over to the left side of this field, the equilibrium position is to the right, and our force flips around the other way. And this is a special kind of force called a restorative force. Once again, like the terminology equilibrium position, this is a very important piece of terminology for this system here. The restoring force or the restorative force. And so let's go ahead and see what happens as it passes through the equilibrium position. It passes through. Initially it's going quite quickly, but it slows down to a stop over here as it gets to a point where it can't push the spring anymore, and it comes to a stop. And during that time frame, our spring force should have gotten much bigger as well, but I'm sorry I didn't animate that. But over here our spring force is back to a very large rightward spring force. And that is our maximum displacement on the left side of this. And if this is done properly, our maximum to the right should equal the maximum to the left, and we should oscillate between these 2 points. And so at the x max point on the left side, the negative x max, the object stops there, turns around, and it reverses its process. So it accelerates back towards the equilibrium position, and then it slows to a spot on the right side of this. So let's watch that happen. Here it goes to the middle, and then it slows down to the end. And it does this over and over and over again if we don't have any friction slowing us down in the system and bleeding off our energy. So we would call this periodic motion. It's moving back and forth and back and forth. And we could actually measure how long it takes to go back and forth each time. One round trip is the period in t, that we use the variable for t, capital T, and that would be in seconds typically. So let's answer some more questions here. So how far to the left will the mass move? Well, we already said it should move. If we start over here, it should end up over here. And we can actually use conservation of energy to think about that and know that that should work. Where will the object be when its velocity is the greatest? Well, the force is maximum here, and it's speeding up along here. And at this point, there's no force left on it, but it's at its maximum speed right in the middle. Force is drawn down to 0, but it's gained all of its acceleration at that point, and it is speeding along. As soon as it passes that, it starts to slow down again. So this is its maximum point of velocity right to the middle. All right, so that's our maximum point of velocity at x equals 0. Where's the velocity going to be smallest? Well, at the end points where it has to stop to turn around. So it's pretty obvious those are our stop points, our slow points. Now, what about our total energy? Where will the total energy be greatest in this system? Well, don't be fooled here, folks. If this is a closed system, then the total energy is constant throughout for both of these answers. Now, where is our kinetic energy the greatest? Well, kinetic energy is a measure of the speed. And so wherever our speed is the greatest, at x equals 0, that's where our kinetic energy should be the greatest. And the same thing, where should our kinetic energy be smallest? Well, when we're stopped, and we're stopped at either end. All right, so at the maximum x distances, plus or minus. Now, where is the spring potential energy the greatest and smallest? Well, the spring potential energy is the greatest when its spring is fully compressed or fully stretched. It's fully compressed over at negative x max. It's fully stretched at positive x max. And so that's where our greatest potential energy is. Remember, potential energy is 1/2 kx squared, and that is a positive value unless we can take a difference between the two energies, and that's where we get our negative signs from. On the flip side of the coin, where is the spring potential the smallest? Well, when the spring isn't compressed, which would be at the equilibrium position. So we can actually use conservation of energy to find the maximum velocity, which we'd expect to be at the equilibrium position. So let's do that. So the total energy at our x max position, which is going to be right here, should equal the total energy at the equilibrium position right here. So I'm going to set those 2 points equal to each other and see what comes out of it. Now, at the x max position, we have no velocity and we have all spring potential energy. So I'm going to have some u spring over on the left side of this. And on the right side, we're going to have at x equals 0, no spring potential left, but we'll have maximum velocity. So we'll have a kinetic energy component on the right side of the equation. And there those are. If we just plug in some equations for those, and now we can cancel out our halves on here, and we can solve for Vmax, and we get Vmax equals the square root of k over m times our maximum displacement of the spring that we started out with. Okay, so we've learned some important things, that this system is a periodic system, and we figured out its maximum velocity, and we figured out where it goes fastest, slowest, and so on and so forth. So let's take a look at what happens with the forces on this and see if there's anything else we can figure out. So let's draw a free body diagram, and I'm going to draw a free body diagram over. I'll line it up with our x max position, but really it's the free body diagram at any point along here. It doesn't really matter where you do this. And what forces we have? Gravity, of course, acting downward, and our normal force, which would be equal opposite of gravity, Newton's third law. And those aren't going to be so important here because I'm actually looking at figuring out what's happening in the x direction, so we're going to ignore those. The only thing we'd have to worry about is if there was some friction involved. So we have our spring force acting to the left, in this case, if we're on the right side of the equilibrium position. If we're on the left side of the equilibrium position, we just flip this spring force over to the other side. If we did have friction and we're moving to the left along this side of the track, we would have friction opposing our motion. And the question is, what happens to the system if there is friction? I'll tell you right now, it doesn't really affect it too much. It'll just eventually bleed out the system energy, but it's sort of being like on a swing set. If you were to swing back and forth and get your little brother or sister swinging and just not push them anymore, eventually they would slow down to a stop. But that would happen, somewhat slowly, or if it's a lot of friction, it could happen very quickly. And if there's a really lot of friction, like if there was a rusted, frozen bars, maybe they'd just stop in midair, not even move back at all. So let's take a look at what's happening if friction is 0 here. And so we've only got one force acting in the negative direction. We're going to take our traditional axes, negative to be the left direction, positive to be the right, equals our mass times the acceleration of the system. And of course, Hooke's law, if this is an ideal spring, would apply. Be careful, some AP questions will give you a situation where you don't use Hooke's law. They'll give you, for example, the spring equation is kx squared or kx cubed or something like that. And then it's a different situation, so you have to be looking out for that. This is a very special situation that we have here, where we have a force acting on this that's proportional to the distance it's being pulled. And that's what makes this system very, 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 very important, as you'll see. I'm going to solve for x. So I have x equals negative m over k times the acceleration. Now let me ask you, what is the relationship between our position and our acceleration, if you think back to September? Well, the acceleration is the second derivative of our position. And so what we have is this relationship. We have our position as a function of time equals minus mass over the spring constant times our acceleration, which is the second derivative of our position. And this is very important. It's called a second order differential equation. And what this tells us is that our position is actually a function of itself. You take the second derivative of itself and you should come back with a function that matches the position. So these functions should look the same for the position and the acceleration. They should have the same form. So let's think a minute. What type of functions could you take two derivatives of and end up with a function that looks very similar in shape? And then we can just pick out some coefficients inside of here to cancel out this minus m over k, which you see me do. Well, what function do you take the second derivative and get back to itself? Think, think, think. Well, sinusoidal functions. If I have sine of x, if I take the derivative of sine of x, I end up with cosine of x. And if I take the derivative of cosine of x for my second derivative, I get negative sine of x. So I go from a sine of x to a cosine of x and back to a negative sine of x. And I can handle the negative sign with my coefficients out front. In the same sense, I could use a cosine function. In fact, for this problem, because I'm starting at a big positive number, not at 0 like sine does, I'd probably want to take a cosine function to model this, not a sine. Because at time 0, I have my largest positive value, just like cosine does. And so I'm going to use a cosine function here. And why am I going to do that? Because cosine, if I take the first derivative, I get a negative sign. And if I take the second derivative, I need to get back to the x equation again. And I do. The derivative of negative cosine goes back to a sine function. It does have a negative sign in front of it, but that's okay. So we're going to use this general function a cosine of omega t for our function that we're going to plug in for x of t here. And we'll see how it works out. But first, let's go ahead and take the first and second derivatives of this function and see what we get. Remember that the first derivative is velocity, so x prime of t equals negative a omega sine omega t. Derivative of cosine is negative sine, and the derivative of what's inside using chain rule is the omega. That's where that came from. I can repeat this process using acceleration. So taking the derivative of sine is cosine with no sign change, so I keep this sign down here. And chain rule, I've got to take the derivative of what's inside and bring that up front, which is just another omega, so I get omega squared here. Now here's what I'm going to do. I'm going to take my original equation, and I'm going to use it to find my amplitude of this function and my angular frequency. Well, my amplitude is pretty easy. My amplitude is just my maximum values. It's going to go way over here, back to 0, then way over here, back to 0, way over here. So from here to here, which is x max, that is my amplitude. And so x max is my amplitude for this function. And it's positive x max because I'm starting on the positive side. Now, as for our angular frequency, what we're going to do is we're going to take our equation here, I just copied it down here again, and I'm going to substitute in my chosen function in here and then do a little cancellation and see what happens. So for my x of t, I have a cosine omega t. So I'll take that and I'll substitute it. And there's that substitution. And for my x double prime, using our special equation here, our x double prime turned into this value. So I'm going to take this and I'll substitute it down below. Let's see what cancels. Several things cancel here. First of all, the a's cancel, the amplitudes cancel. Secondly, our negative signs right over here, they cancel. And lastly, we have cosine omega t on both sides, so we'll cancel both of those things out. Let's simplify, see what we get. This is nice. We've got a nice simple relationship that relates our angular frequency, omega, with m and k. So let's go ahead and solve for omega and see what omega is in terms of m and k. And what we get is omega equals the square root of k over m. And that's our angular frequency or angular speed of our motion of this object back and forth. All right. Now, we can also use a nice relationship that we know and love. If we use omega equals 2 pi f and f equals 1 over t, we can solve for the period of this function. How long does it take to go from x max over to minus x max all the way back over to x max for this little system? And our time it takes to get over there, our period, is 2 pi square root of m over k. Wow, this is a pretty important system here. So we've got a periodic motion going on here, and there's our period. Let's just take a look. Let's give a little overview of what we've seen here. So we've got this system, the spring mass system is what this is called, a spring mass oscillator. And it starts over here, and it's going to oscillate back and forth in a periodic motion. We figured out what that period was. So we found that using this function, x of t equals a cosine of omega t, it seems to predict what that motion is fairly nicely. In fact, if you think about it, that's the same equation we came up for uniform circular motion. This left and right motion of something moving around in a circle matches exactly the left and right motion of this object cycling back and forth. And so that's an amazing result here, is that this spring mass system moving back and forth looks like the x component only of something moving around in a uniform circular motion. And if you don't believe me, what you can do is you can actually in the lab set up a spring mass system and run it through LoggerPro, and you'll see this happen. And we calculated that the angular frequency of this is the square root of k over m. And so if we plug that in, we can simplify a bit, and here's what we get for our position versus time for a spring mass system. They give you this equation on the AP exam formula sheet, so you don't need to memorize that. And all you do need to know is that in uniform circular motion, we need to be able to break down our x and y directions into a cosine omega t and a sine omega t. Remember, our amplitude here is the radius of the circle, and in this case, it's the distance, our maximum distance we're displacing for the spring. It's x max. And so that's as simple as that. And of course, we can take the first derivative and second derivative and plug things in. And there's our period for this function. Here's our velocity, taking the first derivative and plugging our coefficients in for our amplitude and our angular frequency. We come up with this relationship. And remember, you don't want to memorize this. You just want to know that this is on your formula sheet. And you just need to know this is for our circular motion, we have an amplitude, which is the radius of the circle, or the displacement here, times cosine of omega t. Take the derivative of it real quick, and you'll find this equation. You can plug in your omegas. Now let's take a look at this velocity for a second here. We already know that in a system, we swing over here, we slow down to a stop, turn around. Our force of our spring is really big over here, and the force of the spring drops down to 0 here, but in the meantime we're accelerating here, and then here we're at our maximum velocity. Then we reverse that process over here. So our maximum velocity happens at the equilibrium position. And so let's go ahead and let's see how we can do that, plugging into here, and just check to see what the maximum velocity is. So when x equals 0, our angle up on our circle has to be some value that's related to a 90, a 270 degree, etc. And so, because at 90 degrees, we're back at our equilibrium. And of course, if we plug 90 degrees into our sine function here for our angle, it turns into a 1. This turns into a 1. And so what do we get for our maximum value then? What we get for the 90 degree point up here, when we're passing through from the right side to the left side, we get a negative x max squared of k over m. So the negative meaning is moving from right to left. And if we do the same at the 270 degree point, coming down to the bottom right here, it's moving from left to right in the positive direction, and sine of 270 gets a negative times a negative is a positive. And so that's our results for our maximum value of velocity. Well, that's no surprise, because we already did that in conservation of energy and saw that. The only problem with conservation of energy, it can't tell us what the sign is, but we can use some logic and judgment to tell what it is. But you'll notice with our parametric equations, we get sign values in here, or signs as well. The pluses and minuses all work out for us. So pretty impressive so far. And once again, we can take our velocity function and take the derivative once again and come up with an acceleration function. So what actually causes this simple harmonic motion? Well, the thing that causes it is these special forces and the way this is set up. First of all, we need this restoring force or restorative force. We always have a force that's pulling towards our equilibrium point here. We need that. And we also need a special type of force. All right, and the special force that we're looking for is this force right here, which is due to Hooke's law. And it turns out that gives us a proportional relationship between our position and our acceleration. That's our constant of proportionality, and that happens because we had a Hooke's law situation here. And that led us to a second order differential equation, and that allowed us to work out what type of function do we take two derivatives of to get back to ourselves. Well, a cosine function for this case, because we're starting in our maximum value. If we had a different situation, we might use a sine function and just flip this around a little bit. So going back to one of our pre-chapter worksheet problems, let's take a look at a specific function, x of t equals 1/2 cosine of pi t, and see what it looks like, and maybe draw some relationships over to the spring mass system we just left on the last page. So first, let's find a velocity and acceleration. Well, let's just take the derivative. And once again, this looks very similar to the equations that we worked out in the last page for a spring mass system. This would be our amplitude, maybe 1/2 meter, and this would be our angular frequency, omega. So what we can do is take the derivative of this, and the derivative of 1/2 cosine pi t. Derivative of cosine is negative sign. The half just pulls down front. The derivative of the inside comes right up front here, and we still maintain the same exact frequency for our velocity. So you notice the frequency doesn't change between our position and our velocity functions. Once again, for acceleration, we can do the same, and we get a similar result. Now let's find omega. our angular frequency, omega, our period, capital T, and our frequency for these three functions? Well, they're the same for all three. There's our omega, omega, omega. And so let's just take that pi radians per second, and let's use our little relationships that you know and love. Omega equals 2 pi f, and f equals 1 over t. And plug and chug. So we're going to plug in a pi for omega, and we get pi over 2 pi, or 1/2 hertz. Remember, hertz can also be interpreted as cycles per second. So we have 1/2 cycle per second. So in other words, every second we move half a turn for this particular system. We can just take this reciprocal of that to figure out our period, and our period turns out to be a nice round 2 seconds. Let's go ahead and take a look at some graphs of these functions now. So here are the graphs of these three functions, and this is questions 9 and 10 on your worksheet. And so we've got our periodic function here, and here the point is at time 0, and I guess this would be negative time, positive time over here, and it's at a maximum value. So it's starting on the right hand side of our circular wheel if we were on a wheel. So it'd be starting over on the right side. And remember, we're looking at the x-axis is this way. So this is moving. This is our 0 point, our equilibrium point, moving up and away from the equilibrium in a positive direction, moving negative direction, positive direction, negative direction along the x-axis. So our amplitude of this is 1/2 meter. Our period, as we showed, was 2 seconds, and sure enough, these are half-second intervals. There's 1 second, 2 seconds. There's our maximum displacement, and at time 0 for a cosine function, we should be at our maximum displacement. And this does look like a cosine function. We start at a high point, go to 0, go to a low point, go to 0, go to a high point, and so on and so forth. There's our leftmost point on our motion back and forth along our axis, and that's our negative x max. And here's an equilibrium point we're passing through. So let's go ahead and take a look down below at our other functions here and see how these points correlate to our other functions. So for our velocity function, if you take the derivative, we found out it's negative 1.57 sine of pi t, and here's our amplitude of 1.57, and our pi, our angular frequency, is the same, and it gives us the same time frame for our period in each case, t equals 2 seconds. For our acceleration function, take the derivative again, and there's our new amplitude, 4.93 meters per second squared, and there's our period. Period remains the same in all cases. So let's compare these points, these special points here that I selected, and see if things are consistent and make sense. Now remember, at our maximum point, maximum distance away from the either end of our spring mass system, for example, we would have 0 velocity. So if we follow this down, sure enough, there's our 0 velocity. At the same point in time, if we're on the far right side, we're pulling our spring mass system to the right, our spring is pulling as hard as it can to the left, so we should have the maximum acceleration to the left. And here's our maximum acceleration to the left right here. All right, so sure enough, these line up perfectly. Let's take a look at when we're at the other end of the spring mass system on the far left side. Well, once again, we should come to a stop again, and sure enough, we're at a stop point again. And now the spring should be pulling us in as hard as possible to the right, and it is. There's our maximum pull to the right, which is giving our maximum acceleration to the right. For our equilibrium point, we'd expect that's our maximum velocity, either in the positive direction or in the negative direction. And we can look over this side and see the negative direction, and sure enough, it is. There's a maximum point there, and if we were to follow this one down, we get a maximum in the negative direction. And we also said at that point, our spring is not being pulled or pushed, and so we should have no acceleration, no external forces acting at that point in time where we're crossing through that equilibrium point. And sure enough, look at the acceleration down here, it's 0. All right, so everything is consistent. So what conditions must you have for this special type of motion, which we call simple harmonic motion? And simple harmonic motion is basically something that oscillates back and forth, and it matches the motion of either the x motion or the y motion, or perhaps both, of an object moving in uniform circular motion. That is simple harmonic motion. The first thing we need is a restoring force. We need something pulling us back towards our equilibrium position. If we're on the right side of it, it'll pull us back to the left. If we're on the left side of it, pull back to the right. If we're above it, it'll pull us back down. If we're below it, it will pull us back up. For our spring mass system, here's our equilibrium position. And where we are right now, we should have a force pulling us to the left towards it. In fact, we're the furthest point away, and we know how springs work. The more we pull, the harder it will be to. The harder it pulls on us, the bigger the force. If you look at a later point in time, for example, I'm not quite as far over, I have a smaller force, and it's acting towards our equilibrium position again. It's a smaller force because if we push it less, it'll push less on us. And remember, Hooke's law does come into account here. The second thing that has to happen is that our position, our x or y position for our system, and this is an x system, it must be proportional to the acceleration of the object. And we find that out by applying Newton's second law and seeing what happens to the forces. And as you recall, what we found out is that we used Hooke's law, and that was our net force acting on the system. And we set that equal to, in Newton's second law, it's mass times acceleration. Solve for x, our position, and we find out that our position is directly proportional, here's our constant of proportionality, to our acceleration. And that happened because this is a Hooke's law situation. If we have any other situation that's similar to that with any other system, then it turns out that we'll get a second order differential equation again, and that second order differential equation leads us to the sinusoidal motion. Either a cosine function in the x direction or a sine function in the y direction. So, which of these situations are simple harmonic motion? Well, all of these ones here are. And we already saw our spring mass oscillator. It turns out pendulums, in certain circumstances, are simple harmonic motion or not. And I'll explain in a second what special condition you need. If you get a tube of fluid and you started that fluid in motion, it turns out that deals with simple harmonic motion. Now, unless you want to get into some fluid dynamics, which we haven't studied, I think that's in chapter 14, back one chapter, you could actually figure that out. There's another type of system called a Helmholtz resonator. You can look that up and see what that does. So a simple pendulum that exhibits simple harmonic motion has to be small angles. This angle has to be less than about 15 degrees. And we already discussed on your homework worksheet what happens when you have a small angle. When we have a small angle, it turns out sine of theta is approximately equal to theta. We can do a little substitution, and it turns out our mathematic works out to be the same as a spring mass oscillator. It turns out we can turn our spring mass oscillator on its side and just hang a spring from hang a mass from a spring, and wherever it just sits at equilibrium not moving is what we call our equilibrium position. And then if we disturb it from that point, it can move up and below, and it'll have that force of the spring pulling it back to its equilibrium position. And it turns out we get a y situation for our spring mass motion equations. So all of these situations above would give us that nice sinusoidal setup where we have uniform circular motion type of equations. X equals cosine of theta for something moving left and right in the x direction. Y equals sine of theta for something moving in the y direction, where theta equals omega t plus, if you started at an odd point, plus some sort of phase angle. So the simple pendulum at small angles is another classic example. The proof is very, very similar to a spring mass oscillator. It's shown in the book in section 15.4. You can go look at that. And once again, the key to solving that problem is for small angles, this is a simple harmonic motion system. Beyond small angles, it doesn't. It doesn't look like this type of motion over here. And so when we use a small angle approximation, as long as you don't push the person on the swing too hard or too far, you end up getting this situation. And then if you solve that for the period, it's 2 pi squareds of L over G. And if you remember our lab experiment that we did, you figured out that the only things that affected the period were the length of the rope, your pendulum rope, not the mass of it, and not how hard you pushed it. And it turns out that is correct. And this is a special case for a small angle case. But remember, gravity does affect this as well. We just couldn't test for gravity. So you can think of real life at Canopy Lake Park, for example, with the Parada and the extreme frisbee follow these equations. Turns out they do pretty well, even though their angles are a little bit big for the small angle approximation. It still works out very closely to this uniform circular motion type of model with simple harmonic motion. Just some examples that are not simple harmonic motion, and you should know this because they test you on these types of things. So like I said, a pendulum that's swinging at large angles deviates from this, and you'll get some errors, even though you could use this as a model that's somewhat close. Bouncy super ball that's perfectly elastic, that would bounce up and down, and because it goes the same height every time, it would take the same amount of time to get back down to the floor, which would be a perfectly periodic system. But if you looked at the mathematics behind it and the physics, it turns out we don't get that relationship, that proportional relationship between the position variable y and its acceleration ay that we need to make it simple harmonic motion. So it is not simple harmonic motion for a bouncy ball. So let's go ahead and try an AP free response question next.